Hi, welcome to Elementary Functions. Today we're going to talk about trigonometric functions. My name is Wendy Fresh. I'm from Portland Community College and this is Math 112. So let's start by talking about the unit circle. First of all, we know that circles are everywhere. A really great example is this Ferris wheel. The circular motion repeats itself on a regular basis as riders move around the wheel. They move from point to point on a circle. So we're going to consider this unit circle. And what is a unit circle? You can see in the green box there that a unit circle is a circle that has radius 1. And for a while, that's what we're going to limit our conversation about. Now notice that t is the angle. So we say since t can represent any angle measure, as the point moves around the circle, its value changes. So right now we see the point 0, 1 up at a 90 degree or pi over 2 radians. The question says identify the location of the points for some of the following angles. So let's take a look at a few of these. If t is equal to 90 degrees, then the point is at 0, 1 on the unit circle. So that goes along with what we just said. If t is equal to 180 degrees, then what is the point at? Well, let me go ahead and move that point. So that would take us to right here. And so starting at the origin, I would move to the left 1. So that puts me at -1. And I'd go nowhere on the y-axis. And so that would put me at -1, 0. 270 degrees, I keep going. I'm at 270 degrees or 3 pi over 2. And that's going to put me at 0, -1. And how about 2 pi? That's going to finish out our rotation of the circle, and that's going to put me at 1, 0. And of course, 0 degrees is going to be the same location, just didn't go anywhere. And how about -90 degrees? Well, -90 degrees we know is starting on the positive x-axis, and because it's negative, now we are moving clockwise, so that's going to put me right there. And it looks like that value is going to be the same value as 270 degrees or 3 pi over 2. So we should be at 0, -1. While the point values of common angles may be easy to determine, the point values of angles that do not lie on an axis requires some geometry. So let's talk about 45-degree angles. We can see in the picture where that 45-degree angle is. And if you consider the following quadrant of this unit circle, notice that a perpendicular line was dropped from x, y to the x-axis. So what we're going to try to do in this slide is determine what would that ordered pair be. In other words, what is the movement on the x-axis and the y-axis? And whatever that movement is, that's going to give us what that ordered pair is. So why do you think dropping that perpendicular line was useful? Well, my thought is that it's useful because it forms a right triangle. Without that, we don't have the right triangle. We just have the 45-degree angle. And if you recall, the Pythagorean theorem is a nice theorem that allows us to work with right triangles. The Pythagorean theorem says that x to the second plus y to the second equals c to the second. Actually, I guess probably what you learned was a to the second plus b to the second equals c to the second. But really the a and b are just variables that can be replaced with anything. So in my case, I've got x and y. Also, my c squared would be 1. And that's because in this case, that unit circle with a radius of 1 is replacing my hypotenuse. So here's my right angle. Now, if you take a look at this picture, you notice that my x, y has turned into an x, x. Why is that true? Well, the reason is because in a triangle, we know that the sum of the angles is 180 degrees. So if I take 180 degrees, and I subtract out the 90-degree angle that was formed, and I subtract out the 45-degree angle that was formed, that leaves me with 45 degrees. So this angle right here has to be 45 degrees. When I have base angles that are the same, that creates an isosceles triangle. Isosceles triangle. And in an isosceles triangle, if the base angles are the same, then we know that the base sides are also the same. So I said that x and y are the same. I could have said x comma x here, or I could have said y comma y. Either one of those would have worked. All right, so let me go ahead in the place of this y squared, put x to the second plus x to the second equals 1. And now that I have just one variable, I can solve for x. So I get x to the second is equal to 1/2. So x is equal to plus or minus the square root of 1/2. Well, the square root of 1 is 1, and the square root of 2 is 2. And of course, I'm always going to rationalize my denominator if I can, so I'll multiply by root 2 over root 2. And so I end up with that x is equal to plus or minus the square root of 2 over 2. And because we said that x and y are equal, this is not only the value for x, but it's also the value for y. So how do we determine whether it's a plus or a minus? Well, the answer is the quadrant that we're in. So a 45-degree angle is in the first quadrant, and what we know is that in the first quadrant, not only are the x values positive, but so are the y values. So I sort of wrote over that. Let me see if I can get rid of it. There we go. So here is the summary. If t is equal to 45 degrees, or in radians, that'd be pi over 4, then the point is at root 2 over 2, comma root 2 over 2 on the unit circle. So what our goal is on the previous slide we saw some of the ones that seemed obvious to us that were right on the axes. We're trying to determine what are some of these point values on locations that are not on the axes. So let's look at a couple of other common ones. Now let's look at 30-degree angle. If we look at the following unit circle, since this is a unit circle, notice in my picture it says R, but because it is a unit circle, we can go ahead and fill that R in with a 1. We can look at the triangles together, or we can look at them apart. If they're together, then we have formed an equilateral triangle. And what's important about that is that an equilateral triangle tells us that all of the sides are equal. So that's nice. That means that, let me change my pen color here, that if this radius is 1, then this radius is 1, and then this side is also 1. And so if we break apart the triangle, we see that these two guys here, the y and the y, they must add to 1. So we can say that the radius is equal to 1, which is the same thing as 2 of those y's. All right, and now the Pythagorean theorem comes into play again. By splitting the triangle into the two triangles, right triangles are formed, and the Pythagorean theorem can be used to solve for the unknown side. So let's see, what's that going to look like? Well, the Pythagorean theorem, of course, is x to the second plus y to the second, and in our case is 1. And we know something about y. Let's see here, what do I know about y? I know that y is equal to 1/2. So I'm going to say x to the second plus 1/2 to the second is equal to 1. And by the way, on my picture, I don't have x, but I hope that you are okay with recognizing that the x is right there. So let me finish solving for x. I'm going to have x to the second plus 1/4 equals 1. X to the second equals 1 minus 1/4. x to the second equals 3/4, and I'm running out of room, so let me move right here. So x is going to be plus or minus the square root of 3 over the square root of 4, which is 2. So I don't have to rationalize the denominator in this case, and I know that because I'm in the first quadrant that for the x value I'm going to go with the positive version. And so now that we know x, we should be able to solve for y. So let's see here. If I have the square root of 3 over 2 squared plus y squared, and that equals 1, then if I square the x value, I get 3/4. And again, I'm running out of room. So y to the second is equal to 1 minus 3/4. Y to the second is 1/4. So y is going to be plus or minus, what's the square root of 1? 1, and the square root of 4 is 2. So that one turned out nice. So it looks like, let me just go up here, our goal was to find out what is this x comma y, and I think that we've done it. The x value is going to be positive square root of 3 over 2, and the y value is going to be 1/2. So let me see if I can summarize that for you now. There it is, and I'm going to go ahead and erase all of my writing so that you can see it. If we have a 30-degree angle, which is equivalent to pi over 6 radians, then the point is going to be at square root of 3 over 2, comma 1/2 on this unit circle. And finally, the last one we're going to look at is a 60-degree angle. And because the triangles within the 30-degree angle also have 60-degree angles, so what I did is I just took the picture that was on the previous page and I rotated it. A similar argument as the previous slide can be shown, and I'm going to go ahead and just conclude that if we have a 60-degree angle, then what happens is that the x and the y values just reverse. So here's the summary and a nice picture for you.